just for fun, I thought we'd do some extra example problems, dealing with energy conservation and momentum. Sometimes you've got to look at two different parts. So right here, we've got this projectile. Projectile is going to hit this block right here. It's going to go ping, and it's going to embed itself in the block, and the block's going to go up the ramp. All right, and I want to figure out how fast is that projectile going to get to a height h. Well, you need to work with what you know. So if I were to describe this problem, I would describe it in two parts. Block gets hit by the projectile, and the block and the projectile go up the ramp. I know more about the last part, so let's start there. And that's another way to think about it. Divide the problem in the way you would talk about it. Okay, divide the problem in the way you would talk about it. So here I've got this block going up the ramp. No external work is being done by non-conservative forces, so I know that energy is going to be conserved. At the end, I've just got gravitational potential energy. At the beginning, I've got kinetic energy, where this VAC is after the collision. All right. So when you break a problem up, you've got to figure out what carries from piece to piece. In this case, this velocity is the velocity after the collision. So let's solve this. Oops. And the way I would say, oh look, I just get my velocity after the collision has to be the square root of 2gh. Not too bad. All right. Now I know in the collision, momentum is going to be conserved. So initially I've just got some momentum from this projectile, and at the end I've got both objects, the projectile and the big block, moving at this velocity after the collision, which I found from conservation of energy in the second half of the problem. So if I insert this value into here, substitute it in, I get an expression for how fast that projectile needs to go at the beginning. So talk about the problem and divide the problem into parts based on how you would describe it. A lot of times you'll have a collision where you use momentum conservation, and then either a before or after criteria where you use conservation of energy. Now this example is going to be a little bit different. We drop the block. Little block M goes down. Perfectly elastic collision. Bounces back up, and you don't know theta. All right. So how did I describe this? I said block M fell down the ramp. All right. If block M fell down the ramp, I can figure out that I know no external work being done, work done by non-conservative forces. Initially, it has gravitational potential energy. At the end, it's got kinetic energy after the ramp. All right. So now I have expression for how fast the little block M is going after it slides down the ramp. All right, good. So that covers that. Now we're moving into the collision. The blocks hit. So block M slides down the ramp, and now they hit. So if they're hitting, I know it's momentum conservation. So initially, little m has some momentum. At the end, both do. Two unknowns. But I said it was perfectly elastic, which means we can track all of the energy. And then, change in energy is 0. Energy initial equals energy final. Initially, only the little block has kinetic energy. Finally, they both do. And now I have an expression for momentum. And so this is my delta P equals 0. And now I have delta E equals 0. And I can E is not a vector, it's a scalar. Sorry. Got a little, I don't know, I just drew an extra arrow. Sorry about that. So now, we will combine these two equations. If it is a perfectly elastic equation, you can go through and you can math it out. I encourage you to look at equations 13.10 in the book, where they go through it and derive expressions for perfectly elastic collisions. You can do it yourself. I recommend doing that, but verify your answer with 13.10 in the book. Brief aside on how you get 13.10. All it is, conservation of momentum, write your momentum expression, and conservation of energy, write your energy expression. And then you just solve for, say, one of the velocities and put it into the other equation, substitute it in. There are squared terms, it's a lot of terms, but you can do it. And now back. So, if I take 13.10, I don't have any velocity for block B initial, so that goes away. That's nice. And I can figure out how fast A is going after the collision. And I get this nice little expression. So the velocity of A final after the collision is negative 3/5 the velocity of A after the ramp. Negative 3/5. Why is it negative? Oh yeah, it's going the other way. Right? Negatives are just direction. And now to find S. Back to conservation of energy. So we covered M goes down the ramp, it hits, and now we're going to the part where M goes back up the ramp. So now it's an energy problem. Initially it's got kinetic energy, and then it winds up somewhere at the top of the ramp. Still don't know theta, but don't worry about it, because when we derived our expression for the velocity after the ramp, it included sine theta. So we'll take a look at that. Oh, look, those sine thetas are going to go away. Oh, that 1/2 is going to go away. The g's are going to go away. And you get 9/25 of your initial height is equal to your final height. It's a lot of substitution. So the key parts of this, you break the problem into parts. How do you know where the parts go? I would just say like you're telling a story. And whenever you come to a new sentence, it's a new part of the problem. Try to avoid and run-on sentences when you do that, by the way. Otherwise, it gets really complex really fast. But you'll have energy conservations. You can always use that if you can track all the energy. Momentum conservation when you have a collision. So that moment of the collision is always going to be one of your parts. I hope that helps. If you have any additional questions, please ask, and I will see you in class.